Parametric equations. What are they and when do we use them? Parametric equations are typically when we need to express a third, another dimension, basically. So if you think of like a particle moving through space, we can locate its position using x and y. That can define its position. But if we need to know what direction is it moving, we need a third variable like time. Like where is it after 1 second, where is it after 2 seconds, where is it after 3 seconds? If we can plot that, we can show direction. So when we need to show movement and direction, we introduce a third parameter or variable called time. And this is mostly most of the ways that we will use the application of parametric equations is when we need to express movement and direction. So, for instance, here's the first example that will help us know about this. Construct a table of values and plot the parametric equations. X of t is t minus 3 and y of t is 2t plus 4 from -1 to 2. All right, so we've got x of t is t minus 3 and y of t is 2t plus 4, and we're going to do this from -1 to 2. I'm going to do this from 0 to 3 because I want t to stand for time and I want to talk about positive time. So let's do this one. If we want to construct a table of values for t, we would just say, okay, here's t. Okay, and here's what is x going to be. X of t is dependent on t, and y is also dependent on time. All right, and I'm going to remind myself that this is t minus 3 and that this is 2t plus 4. When t is 0, 1, 2, and 3. Okay, when t is 0, x is negative 3. When t is 0, y is 4. When t is 1, 1 minus 3 is negative 2. When t is 1, 2 plus 4 is 6. When t is 2, this is -1. When t is 2, that's going to be 4 plus 4 is 8. When t is 3, this is going to be 0. When t is 3, that's going to be 6. Plus 4 is 10. Okay, here we go. Let's plot this, and then we can see the movement of our particle as well as not just the places it has been. This is x, and this is y. Okay. When time is 0, it starts here at the position -3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Negative 3, 1, 2, -3, 4. Starts here. This is t is 0. Okay. And then after 1 second, it's at -2, 6. These are the coordinates. Okay, so then at -2, we're at 6. Here, this is t as 1. And then at -1, and then after, when t is 2, we're at -1, 8, -1, 8, we're right here. And then we're at 0, 10, right here. So we're at this position, and we can see the progression of it, right? From here to here, it shows the direction that our guy is going, that our particle is moving. It's moving in this direction. So we could have a line there with just x and y, but we wouldn't know if it was going from down to up or from up to down or back and forth even. So this tells us what's happening here. All right, let's look at another example. What if we have to find a pair of parametric equations that models the graph y equals 1 minus x squared, and then plot some points and sketch it. So let's do this one. This will be interesting. This is example 2. What if we've got, we got to find a pair of parametric equations that models y is 1 minus x squared. And so what we're going to do is we're going to let x, which is dependent on time, equal to t. All right. Then y, which is also dependent on time, equals to 1 minus x of t, or just t squared. So these will model our equation. So we could do, again, we could do a table of values, 0, 1, 2, 3. All right. And wait, did they tell us when to do it between? No, they just said plot some points. So let's do x of t and y of t. All right, let's see what these will look like. At 0, y is 1. No, x is 0. At 1, x is 1. At 2, x is 2. At 3, x is 3. Okay, when x is 0, y is 1. When x is 1, y is 1 minus 1, which is 0. When x is 2, y is 1 minus 2 squared, or 1 minus 4, or negative 3. When x is 3, 1 minus 9 is negative 8, is what we get there. So let's plot the progression here. This is the point 0, 1. This is where it starts. So we're at 0, 1. All right. T is 0. And then when time is 1, we're at 1, 0. T is 1, we're at 1, 0. And then when t is 2, we're at 2, 2, negative 3. Okay, 2, negative 3 will be down here. This is t is 2. So after 1 second, we're here. After 2 seconds, we're here. After 3 seconds, we're at 3, negative 8. We're like here. T is 3. So this shows the progression of our particle over time. So that's the benefit of parametric. It shows where it is and where it's headed at what time. Let's look at the next one, which says to parametrize the curve given by x equals to x cubed minus 2y. So what we have to do is what we just did, but it's a new way of saying it. Like what we did in this example, 2, was to introduce a parameter. That's what they said. Here's another way of saying introduce a parameter, parametrize the curve. So let's try that. Example 3 goes like this. Parametrize the curve at x equals to y cubed minus 2y. Okay, if we want to do that, what we can do is we can let's let y equal to t this time, or y of t equal to t, okay? And then, what will that do? Well, then x of t will be equal to t cubed minus 2t. And we can parametrize the curve that way. We could do the same thing where we built a table of functions and let t equal to some different values and figure out what y is and see the progression of that. We could do the same thing we did there. All right, let's get one more example where they want us to write parametric equations for something more involved. This is an ellipse. So this is something we can do when we have an elliptical situation. This is example 4. What if we have this? X squared over 25 plus y squared over 49 is 1. So this is an example of an ellipse. For those of you who have already had pre-calculus, hopefully you recognize this equation. Okay, so if you have something like this, we can rewrite this as a parameter, and we could do the same exercise where we let x be t and solve for y, but here is another approach when we have something of this form. We could recognize that 25 is 5 squared, and we could recognize that 49 is 7 squared. But even if we didn't, we could write whatever number that is the square root of something. It wouldn't have to be a perfect square, but this is a nice one to notice. And so then we could rewrite this as x over 5 squared, and this is y over 7 squared is 1. All right, this is fine. This is good. Also, we could notice that we could maybe think about trig, which we're in trig right now, so that's kind of nice. We could think of this Pythagorean theorem, the sine squared of theta plus the cosine squared of theta is 1. And these look similar. Something squared plus something squared is 1. So here's what we could do. We could let x of t equal to the sine of t. And if we let that happen, or I'm sorry, we could let x over 5, in this case, x over 5 equal to the sine of t. And then we could let y over 7 equal to the cosine of t. And then we could rewrite this equation as sine squared of t plus the cosine squared of t is 1. And we've parameterized this curve. We can solve for x. X here, multiply both sides by 5, is going to be 5 sine of t. Solve for y. Y is going to be 7 cosine of t. So now x is a function of t and y is a function of t, and we have parameterized these curves. Now, we could have chosen to have written this as, we could have let x over 5 be cosine of t and y over 7 be sine of t. We could have also made that choice, okay? And what that would do, though, it does affect the direction that it moves. We would get the same ellipse. What will happen is we'll get the same ellipse if we plot this guy. But what's going to happen is the direction of movement will be different according to how we define this. So if we know the direction of movement and we want to write it according to that, we would choose carefully what we let be x and what we let be sine and what we let be cosine in this situation. Okay, last example, last two, but they're quick examples, is what if we have to get rid of the parameter t? So that's not too hard. To get rid of the parameter t, this is what we do. So if we have a parametric equation, but we don't want the third parameter anymore, we just want x and y, then it just becomes a matter of some algebra. It goes like this. Just a second. Make a little room on my thing. Okay. It's getting harder to erase this board. Okay, so what if we want to get rid of the parameters? We can also do that. If we've got x of t is 5 plus t. This is example, what was that one? Let me count. My sheet is not cleaned up yet. 1, 2, 3. I think this is 4. I hope this is right. Okay. And then 5. Oh, this will be pretty quick. We've got to get rid of the parameter. So we've got x of t is 5 plus t, and y of t is 8 plus 3t. Well, this is pretty simple. What we'll do is we'll just solve for t. So first thing I'm going to do is get rid of this of t and just write it like this, okay? And I'm going to solve for t here. So I'll subtract by 5 and I'll get t is equal to x minus 5. Okay. And then I'll just make a substitution in here. Instead of t, I'm going to put in x minus 5. So y becomes 8 plus 3 times x minus 5. Or y becomes 8 plus 3x minus 15. Or y is 3x minus 7. So now I have y in terms of x, and I don't have a third parameter t anymore. So you can get rid of the parameter if you need to. Here, we're going to do it again here. Here's example 5. We have x of t is equal to 2 times the square root of t, and y of t is 5t minus 3. Okay, so let's say get rid of the parameter, get rid of t. So what we did, we're going to do the same thing here. We're going to solve for t. The issue here is, we'll start off the same. Get rid of this of t stuff. So we just got x is 2 times the square root of t. So we could solve for square root of t right here. X over 2 is the square root of t. Okay. Here's one thing we want to pay attention to. Remember how it mattered in the last equation how if we let x be sine or y be cosine, or y be cosine, or vice versa, it made a difference in the direction of movement. With this, you have to be a little bit careful. Notice the domain here. The domain of t, you can only put a 0 or positive numbers under a square root. So that will affect the domain of x, okay? So we want to pay attention to that. T has to be greater than or equal to 0. That means that x, what we'll get for x, it will always be greater than or equal to 0. So even when the parameter of t is gone, the domain that it came from will affect our equations that we end up with. Okay, let's solve for t. Square both sides. So what we do is, what we'll get here is x squared over 4 is equal to t. And then we'll substitute this in here. So we get y is 5 times x squared over 4 minus 3. Y is equal to 5 over 4 x squared minus 3. This is a parabola that's been shifted down 3 and stretched vertically by 5/4. But here's the deal. We're going to plot this, but it will only be the right side that gets plotted because the domain of x was affected because what we started with t. So we have to pay attention to that. All right, that's parametric equations.